Hi everyone and welcome to today's 1W-minds talk. Today's speaker is Karin Schnass, professor at the Universität Innsbruck and a former organizer of the 1W-minds seminar. She obtained her PhD in 2009 from the EPFL and has been both in Eindhoven, Lausanne, Linz and Sarpsborg before joining Innsbruck. Her research is in the field of signal processing and applied functional analysis, not the least dictionary learning. The latter will likely play a big part today. The title is Dictionary Learning Sparse Matrix Factorization. The floor is yours, Karin.
Oh, thanks for the nice introduction and also for having me. I'm very happy that I got this date. So if you've heard about dictionary learning, then you probably know where this is going to go. If you have never heard of dictionary learning, you will after the talk. And just for the moment, this is the explanation. Think of it as sparse matrix factorization. So we're going to go into more details next. So let's first clarify what we want to do. Let's assume we have a couple of vectors. So for instance, we have images, or we have patches of images or audio signals or parts of audio signals. And what we do is in some way, we cut them into pieces of the same size. So you see the pictures have the same size, or the patches, they all have the same size. And then we stuff them into a big matrix. And this matrix is fat, but not very long. So we have much more signals than we have entries in each signal. So let's say if we have images 16 by 16 pixels, then we have 256 black and white pictures, data dimensions, but we have, let's say, if we have a big image database, way more than 256 images. So what we think of is n large, so we think that n is much larger than d. So now we have this massive amount of data or of signals, and what we want to do next is we want to see, can we maybe organize them and find some structure in them that is then afterwards useful to do whatever signal processing task or deep learning pre-processing thing. So the idea is that while maybe these signals have structure, the way we represent structure is saying, okay, there is some underlying amount of building blocks, and these building blocks, we say these are the dictionary. So a dictionary is basically, in our sense, a matrix consisting of k vectors, and if we assemble these vectors in a correct way, and the correct way means these are good building blocks. Of course, I can, with the very small Legos, I can build everything, but it's a hassle. It's sometimes convenient to have bigger Legos, so we need less pieces. So this is what we want to do here. We take coefficients. So for every signal, we have one set of coefficients. So what we want is that we don't need a lot of the possible elements. So every one of these x is sparse. So this is what we say here. Not a lot of the entries in the dictionary, in the coefficient matrix per column is non-zero. So what we want is, of course, if we have a basis, if this were a basis, then here we would always, if we have D options, then we can always find a representation, but we really want that S is much smaller than D, okay? So if you then, just to make things non-unambiguous, we also say that we want our building blocks normalized. This is just to make life easier afterwards. So if you think about it, like we have, before we have our big fat matrix here. So what we then want is that this is, so this is a D times N matrix. So let's figure out where the sizes are. So this should be a D times K matrix, and this should be a K times N matrix. And in the coefficient matrix X here we have the dictionary, and here we have Y. So what we want is that the building blocks that we have is much smaller than the number of signals. Of course, if I make my dictionary, if I take the signals themselves, I can get these things one sparse here, but that, it's not very useful because I don't gain anything. And what we also want is, as you see here, that there's only a few salient entries in each thing. Good. So now our task is just somebody gives me Y, and I want to find something like this. So this is what dictionary learning is. So if we want to do dictionary learning, basically the first thing that we would like to do is we say, okay, well, we have a signal, we have our signals. So what would you like to do? We can just say we want to minimize the error we make if we take any dictionary. So like we take this dictionary here, and that has K elements, and then we take our coefficients, any coefficients that are in column-wise as sparse, and then we say, okay, what's the error that we're making? Let's make a small error. First, we need to discuss how do we measure error, and then we say, well, we could measure what is the biggest error, but what we're going to do here is something, it's like we just take the error that we make with every signal, and then we sum that up in an L2 way, which is basically what you get if you use the Frobenius norm here, okay? So, and why do we use the Frobenius norm? Apart from that, it sort of semi-makes sense, because it's also the only thing that, you know, we can treat mathematically in a nice way, okay? We could do some other things like operator norm, but, you know, in the end, it's a collection of signals. We want the average error to be small, but we could think of, let's measure the 2 norm error in every column and then average that. So these are options, but they are more difficult to solve. So let's stick to easy here. Problem is complicated enough. Why is the problem complicated enough? Because unfortunately, this optimization program is non-linear. It's also non-convex, and in all, the thing is we cannot even calculate some of the gradients if we think about it. So this is absolutely not easy to do, even though we've already simplified. So in particular, if you want to take the derivative with respect to both phi and x at the same time, this is something we are not able to do. There's good news, however. I mean, just because we can't do anything doesn't mean that we're going to stop trying. So the whole problem, the whole optimization problem, is not so bad if we keep certain variables fixed. For instance, what we could do is we could fix our dictionary, say, well, that's now a given. But given this dictionary, what would be the best coefficients? And that is a problem that becomes maybe feasible to solve, or we can do it the other way around. But let's just look first at what happens if we fix the dictionary. So we fix the dictionary. So you can see here now I just optimize over all the possible sparse coefficients instead of here where I also optimize over the dictionary. So if you look at this, then we can just rewrite what we need to minimize in a maybe a little bit more easy to grasp way. So if we look at all the signals that we have, then we have here the dictionary, and then we have here our coefficients. And then we take just the 2 norm of this, and then we square that, and then we sum that up. So if we just rewrite this, and now if you see, we have to minimize over all x, but this x here, this S sparsity, translates to S sparsity here in every column. So basically this whole thing decomposes into n independent problems for every signal y. And what we have to do is we have to solve n sparse approximation problems in our given dictionary psi. Okay, so we get basically n sparse approximation problems. What do we do when we have a sparse approximation problem? Now we can do something sophisticated on various levels, depending on how much information we have on psi. For instance, if you know that psi has a RIP property, which you can never check, but for some reason you might, you know, a genie might tell you, you could do basis pursuit or something like, or lasso or something. Or, and this is something that will always work, you can use the greedy approach or anything to try to solve this problem. So you can use your favorite method, and dictionary learning that starts with and the signal processing community and signal processing people love OMP. So all the algorithms that we will later encounter, they are designed where you use this sparse approximation method OMP. On the other hand, I also love OMP, but there are several reasons why I don't love it in the context of dictionary learning. First of all, it's a bit complicated to analyze, so we don't know what happens. And second of all, it's a bit costly and it's a little bit too greedy. Greedy is good when you know this is the thing that you want, but when you're not so sure that this is the thing that you want yet, because psi might not really be the best thing yet, it's a bit too greedy and not so good. So what we're going to use instead is something that is super cheap and is a little bit easier to analyze, which we call thresholding. It's very, very easy. So basically what you do is you take your signal yn, and then you calculate inner products between all your dictionary atoms. So this will give you a huge vector, okay? And then you sort the vector, and then you say, I want to take the S entries that are the largest in absolute, well, in magnitude. And I will then take the indices where this is largest. And then this is a very simple procedure, and then you can write that down mathematically, and you get this, which looks a bit nasty, but it's really just take inner products, sort them, take the indices of the largest entries in magnitude, okay? So now you get this index set. That would be good. And then you can say, okay, now I know how the optimal coefficients for this index set should look like. I just take the projection onto that. So what you take is here the pseudo inverse, and you project your signal onto, use that to get the coefficients. Huh? So that would give you then the best approximation. And then outside of the indices that you selected, you just set your coefficient vector to 0, okay? So that you get really a coefficient vector that has k entries, even though all apart from S are non-zero. Is there a question so far? Just because now we are done with the thresholding, just think of it as easy. You take the S biggest chunks, and then you project onto the subspace generated by the atoms with these indices. Good. So we can see that is something which we can try to do in this way. Now the next question is, okay, so if we fixed this, we can now calculate, let's say, the sort of best coefficients. But what happens in the other way around? So there's something weird going on here, sorry. Once we have updated the coefficients, we fix x hat, right? So this is now the other problem. Okay, we fixed the x. Now we want a better dictionary. Now, principally, this problem almost looks easy, okay? If we get rid of this weird constraint that you should be a dictionary, so having k elements is not a problem. What is a problem is having normalized columns. Normalized columns is complicated. Okay, so we don't want that. But we can make our problem easy just by ignoring this constraint and say, let's solve that. And then afterwards, we can normalize our dictionary size. So this is what we're going to do. We will just say, okay, it has to have the correct size. And once we have that, we can really solve this with so this becomes a very easy to solve problem using just, again, the pseudo inverse of the coefficients this time. Now let's check the dimensions. What we have is that we have to take y, then we have to multiply with the transpose, and then we have to take x hat transpose the inverse. So we assume that our coefficients are rich enough that this actually has full rank. And then basically, this will be our optimal psi, okay? So as you can see, this is what we do. And then this algorithm where you use this dictionary update and OMP before, or some sparse approximation, this has been around for about 20 years. And it's called the method of optimal directions. And it was invented by Jerzy Engen and co-authors. And it's commonly referred to as the mod. And we will also encounter the mod now during the talk, the rest of the talk. So this is just, sparse approximation, and then, get rid of the nasty constraint, do the obvious thing, and then normalize again the columns in your dictionary matrix afterwards, okay? Good. Then there's other things that we could do. For instance, alternatively, we want to minimize this object here. What do we do if we're in sort of machine learning and we want to optimize something? We use gradient descent, or stochastic gradient descent. But what we do here is basically we do block coordinate descent. So basically we're going to go down in the direction of psi. Sorry, the font. So here is the function that we want to optimize. And because it's a little bit complex, I've already calculated the gradient for you, but we can do the gradient step together. So remember, we want to minimize, so we have to go in the opposite direction. So we take our current guess, and then we go in the opposite direction. So we have to add plus. And then we take a matrix of, so a diagonal matrix of step sizes, lambda, and then we get something. And this whole thing we now have to normalize. So we multiply with some diagonal matrix again that ensures that our psi hat also has normalized columns. And of course, this normalization matrix depends on the step sizes that I make here. So first, we have to take step sizes, and then we find the normalization matrix. Okay, so let's do that. But then we can manipulate this thing a little bit, right? So we can rewrite this and say, okay, I would prefer to have this lambda matrix outside. So I can write this as phi lambda minus 1 plus, and now I just repeat all this stuff. Oh, and luckily I don't need this anymore. And now I multiply with the lambda matrix outside and with the d lambda matrix outside, and I get some expression like this. And now the thing is, okay, this is what I have here. If you compare what is done here with some other famous dictionary learning algorithm from the paper Online Dictionary Learning by Julien Meral and others, and if you say, okay, I can choose the inverse of the lambda matrix, and I will just take the diagonal matrix of my current coefficients correlated with each other. So exactly this here. Then this is exactly the algorithm I get. So it's just basically a type of block coordinate descent with a very specific choice of the step size matrix. Okay, good. And here, the paper is called Online Dictionary Learning, so we will refer to this algorithm as ODL. Okay. So, and then finally, if you go into Google and you put in dictionary learning, there's one thing that will come out, and that's called KSVD. So let's have a look where that comes from. So if we do the coefficient update and the dictionary update, what we can do is we can also just say, okay, now we do, after the coefficient update, a dictionary and coefficient update. But we do it for each atom, so for each column of the dictionary, and for each corresponding line in the coefficient matrix separately. Okay, so what do we mean by that? We have our optimization problem, and then we can write this here in a stupid way, because that's always good. So we can say this is the sum over all the dictionary elements, K. And then we can write this as, take the columns here, and then take the rows here, and I will refer to rows by a superscript, okay? So columns, subscript, rows, superscript, okay? So I can just write this as that. And then I can say, okay, now I'm not interested in any of the columns and rows except for the elf. So, well, I can just write it like this. I mean, here I take the sum over all except for the elf, and here I take the elf. And I can say, okay, let's call this matrix here for the moment E matrix. So this is the error matrix that I make without taking into consideration what the elf atom is going to make, okay? So, and now the only thing I want is if I write this problem here, I can say, okay, there's two types of signals, the ones that use the elf atom and the ones that do not use the elf atom. So let's just split this. So we get E lambda minus, so this is just, we restrict ourselves to the one in in lambda. And then we can have a look at what happens outside. But yeah, well, outside, if we restrict us to the complement of lambda, then here we get the zero vector. So x hat L restricted to the complement of lambda is just the zero vector. So we don't subtract anything. So what will happen here is we just get this error matrix and we take the Frobenius norm. So this is independent of the psi L, okay? So let's rewrite that, okay? So have it pretty again. So what we can do here now is we have to solve this. So this is basically a rank 1 matrix, and we have to approximate this error matrix with a rank 1 matrix. And this is also quite easy to do. You can do this with a singular value decomposition. And you're going to do this for all K of the atoms that you want to update. So you do K singular value decompositions, which basically means you get KSVD, which is one of the most famous dictionary algorithms ever. Okay. Now you can say, okay, I just want to use this for the dictionary update the elf atom, and even though I get here new coefficients, I'm not going to use them. Or you can say I will also update the coefficients, but let's just think of it for the moment, because otherwise it would be super, super hard to just update the atoms one by one. Okay, so is it better to analyze now? No, it's still horrible, 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 because we have to analyze singular value decompositions, and then you have to deal with subspaces and the stability of subspace, and well, hopefully the singular values would be separated enough that there's stability, but you know, this is a nightmare where you actually do not want to go. So the question is, well, but you know, is it also these singular values, I mean, is quite hard to compute, right? So how would you compute it in practice? You would compute it with a power iteration. So what is the cheapest power iteration? Well, you have a pretty good guess of what your new psi L would be. So here you get the starting point, and then you just apply one step of the power iteration, okay? So this is sort of the cheapest power iteration that you can think of. So let's have a look what this super cheap power iteration that we now decide what this is going to do. Well, we can just plug in what is E lambda, okay? So here we just write E lambda, and then here we are going to write E, reduce it to lambda, and then transpose. So reducing takes precedent over transpose. So here what we have is basically we have y minus psi x hat, and then we added the x hat L so that we get E. This is basically just E, if you remember, okay? And then we have to multiply with psi L, okay? So this is now written a bit nicely. So now let's think what happens here, okay? all the things that are in here are signals that use lambda, the elf component, right? So here you have a residual where you project it also away from psi L. So basically what you get here is every one of these, let's call them Rn in here, is actually orthogonal to phi L, because L is in I hat of n, okay? Remember, we projected on phi L, so to get this x hat, so if we now take the residual, it has to be orthogonal. That is basically the best approximation. So if we take this here, we have the transpose here, this will be 0, okay? So we are just left with this part here, but here we have that phi TL with, psi TL with psi L, that is again just the inner product. And we said our columns are normalized, so inner product has to be 1. So if we take all these simplifications, what we get is just this, okay? And then we can again put our definition of E, or first we can say, well, what happens if I add here all the entries that are outside of lambda? Well, absolutely nothing, because they are also 0. So what I can get is that this is the same as if I take also these other vectors inside of lambda complement, and then I multiply them with 0. So basically I can take the whole matrix here and it will not change anything, okay? And then I can say, well, how do I get the Lth row? Well, basically I just multiply from the left with EL transpose the matrix, and then I have to transpose the whole thing around. So what I get is this, okay? Great, and then we fill in again the definition of E, just this, and we get this thing here for our update. And then we can write what this means for the whole matrix. And we get this. So if I take the power iteration, I get this. Who has a déjà vu? Who has seen this already? Sorry, I'm used to being interactive, but I see that there's a problem with the online format of the interactivity. Well, yes, if you think back, this was exactly the update step that the online dictionary learning algorithm was supposed to make. Okay, so if you approximate in KSVD the singular value decomposition with one power iteration, you get back to ODL. So means probably the algorithms are not too different, and if we can prove that ODL is kind of benign and will converge, then we already have a good idea that KSVD will also be benign and converge, okay? So now I've talked a lot about 3 algorithms to you, and then I said, oh, they come with OMP, but I will use thresholding. So let's see, maybe give you some idea how they work and what happens if I go cheap. Oh, sorry. First, we summarize. So just summary what is going to happen here. This just means sorting, taking the biggest, taking the coefficients that correspond to the orthogonal projection, and then fill out with 0 outside, and then here are the update steps for the dictionary. Okay, so this is ODL, as you can see, and then what you return is just a normalized version. Good. So now we're going to some learned dictionaries. So here I take the Peppers image, and then I take all the 8x8 patches that are possible, and then I try to learn something that could be a basis. Okay, but what I do before is I say, okay, something that is constant all the way is going to be present a lot. So I will, just assume that this is a given, and I'll just approximate. I will say the data where I need to learn is this after I've already taken out, let's say, the constant thing, so that the images, the small images that I get, they have 0 mean. Okay, so let's have a look at what the mod and the ODL do, and this here is the versions that use OMP. Okay, so what you can see is, yeah, they give you something that probably is plausible, that this is good to represent peppers, and you know, it captures sort of the structures. It's a quite a smooth image, but then peppers have edges that go from left to right and from right to left. So here, for instance, you can see an edge here, and here you can see something that it can be used to represent an edge here. Okay, and in all, peppers is quite a smooth image, so there's not too much going on here in the dictionary. But then I said, oh wait, KSVD was supposed to work almost like the online dictionary learning thing, like ODL. So let's have a look if that is really true. And if you can compare the two things, they are really quite similar, right? I mean, for instance, look here. It really produces more or less the same thing. These are the same. These are the same. So they all work nicely. They produce something plausible, and they produce something similar, of course, with the same initialization.
Can I ask a
So
question?
then you can ask, okay, Karin, but you use the cheap thing. What happens if you go cheap? So instead of OMP, I now show you what happens if I use thresholding. So here happens if I take the mod or ODL with thresholding, what you can see is not too much of a difference, but there's a little bit more of high frequency stuff going on. If you look here, this one is smoother than this one compared. And the same thing happens also here. For instance, if you see at these ones, what you can see also is that the mod, I mean, you just have a little bit more high frequency stuff going on. But for the ODL, I don't know if you can see this on your screens. I can see it on my screen because I'm much closer. It's a bit more grainy. So admittedly, if I combine with ODL, the thresholding stuff gets grainy. So, but it's not tragic, okay? And then finally, I want to show you there's also some third option where you can just take thresholding and then you do something that's even cheaper than mod and ODL. So you just take averages. And what you can see, also this thing, it's quite similar to everything else, okay? So what you can, just these things are reassuring that, you know, all the modifications were not tragic. The algorithms do more or less the same things, on peppers at least. But if you compare on Mandrill, again, with OMP, so these are the OMP-based ones. And then here you have the OMP-based ones, and here you have the thresholding-based ones. So you can see Mandrill is an image with much more texture. You can see here, there's the hair, so there's edges. So of course, the dictionary tries to capture all this high frequency texture stuff. So there's a lot more going on. So you see there's a lot more high frequency atoms. And again, if you want to see a difference, there is more high frequency stuff if you look at the thresholding based stuff than if you look at the OMP based stuff. Okay, so this is one of the differences. Good. So now I've shown you that they look plausible, but the question is, I mean, not anything that looks plausible is better in practice. So what I plot here is you can say, okay, I approximate with higher and higher sparsity. Sorry, I'm in a smart building, and the smart building thinks that it's now too light, so I need to stop the blinds from going down.
So I think there also was a question. Is the question still there?
Yes, questions.
I think I had a question just now.
Yes.
Which is that in the previous slides with the dictionary atoms,
Yeah.
are the atoms arranged in some order? So, or by some other criteria?
I arranged them in the order of, so this is basically, there's no natural order. It's just the initialization is the same.
Right. So okay,
they all come from the same thing. So
right, so
what would be?
Okay.
Sorry?
No, go on.
So it's the same initialization for all, and it's
Right.
the order of the, I start with some, let's say, psi1 to psi k, and I let it run, and I keep the
Right.
same order. There's no
Okay.
importance ordering.
Okay. So
Okay.
so that explains why, yeah, the atoms there. So like I
Yeah.
guess if you think about the trajectory, the ODL and the KSVD should be quite similar. And
Yes.
that's what we see.
So
Yeah.
exactly, this is saying that, you could think that there's local minima, but we start probably in the same basin, and what happens is we go to the same thing.
Yeah. Okay,
So,
thanks.
and it's just reassuring that locally it more or less does the same thing.
Yeah, okay.
More questions? Because now we're just going to the practical performance. So I take now all the patches that I can extract from these things, both from the mandrel and peppers. And these are the curves that I get for mandrel, and these are the curves that I get for peppers. And I say, I learn a dictionary with mod and OMP, and then I say, this is the dictionary I get. And now I use OMP to approximate with level, with sparsity 1, 2, 3, 4, 5, and so on. And then I plot the average error. Okay. So what you can see is, as expected, the dictionaries looked all the same. They were all doing, they're all doing well. So you can see that there's no difference between the lines. They're all performing well. You can also say that all this whole dictionary business, I mean, there's stuff that's been known for ages, like wavelets and the discrete cosine transform. How good is that? So this is basically the curves that you get here. If you just use something prefabricated, then this will give you this approximation rate. So you can say, wow, good enough for me. And true, if you want to just compress stuff, always use something with a fast transform. But, if you have some more data analysis things in mind, well, why not use some learned dictionary? Okay, so that's good. This is the ones with OMP. But what happens if I go cheap again? So here is again mandrel, here is peppers. And what you can see is that I learned with a sparsity level S in the learning, which is 3, but we already said there is this one atom that we didn't learn. So basically what I said is the average sparsity level is 4. Okay, so this is sort of what I tell the algorithms that they should look for, this here. And what is interesting, if you are below the learned level, the learning level, it's a little bit better to take the dictionaries that are with OMP. And if you go, it starts to become better to use the thresholding, because the thresholding thing says, oh, there is high frequency stuff. We should also have a look at that. Whilst OMP said, take the big thing. But, it just concentrates really a little too much on the sparsity level that I give it, which is okay in some sense, but then I also have to make a choice, right? And I don't know the choice. So what you can see here, also the crossing starts to go, I mean, in the end, it goes under, they are pretty similar. So let's say, all good, we can feel relaxed now about actually looking at these algorithms, will be fine. So it's not early morning anymore, not even in Britain. And I guess in some parts of Asia, for most PhD students, it's always early morning. So we can't put it off any longer. We're going to have a look at a little bit of math with all the stuff that we did now. Okay, so what we would like to do is, our goal is, assume we have a really nice dictionary, and that's called phi, and we have nice sparse signals. So someone has a machine and he's making nice sparse signals. So what is he doing? They take random plus minus 1 coefficients, okay? And then we take some magnitudes, but just for simplicity, think of all of these magnitudes as 1, okay? Just, we choose atoms, we flip a sign, and how we choose atoms is we say, okay, we take a vector, the ones that we choose, we flip them on, and then here we take the pointwise inner product. So this is, we just multiply entries. okay? So this is just tells us which are active. This gives us a random sign. And what is now interesting is how do I choose which atoms are active, okay? So, well, I choose it randomly, which is still a bit vague, but we will get into that a bit later. Okay. And then what do I want to do is I want to characterize the area of convergence. So I will say, okay, now I have the space around my dictionary phi, and I want to know from where do I actually converge to it, okay? So meaning in some distance that I will need to define, I want that after one iteration of the algorithms, I'm closer, and that, you know, this psi hat, if I put that into the machine, all the requirements for convergence are still there, so they are preserved. Okay, so this is what we want to look at. Now here, if you look at these slides, there were a couple of vague things. So there's nice dictionary, and there's chosen randomly, and nice diction, and then there is here some distance. Okay, so we will clarify all these vaguenesses a bit later on, but maybe just start with chosen randomly. Okay. Okay, chosen randomly. So if you say, okay, now I have K atoms and I should choose which ones are active, and that should be exactly S. Well, what you can say is I take all the possibilities of a subset of K, which has size S, and then I evenly select one of them, so uniformly among all random supports of size S. And then you can say, okay, great. Now I can plot what happens, and then basically all atoms should appear with equal probability. And then I can do this with my learned dictionaries, right? I can look at all the atoms I learned, and then I can approximate from before my signals, and then I can count how often an atom is used, let's say, reliably, you know, with a good coefficient. So this is what I did, and I did that for various things of reliable, but in general, you have the reddish plots are for the monkey, and the bluish things are for peppers. But what you can definitely see, if you look at these atoms, then they are not used equally often. There are some atoms that are used a lot. So this one is used basically always. And then, you know, this is a log plot. The frequency with which they are used decays quite strongly, especially for peppers, okay? So in the end, you will see, okay, these are the high frequency ones. They are not used a lot. It makes sense. Why does it make sense? Well, before there was all this dictionary learning, machine learning stuff, there was something called wavelets and the discrete cosine transform and Fourier stuff. And all these things would never have worked for signal processing if there was not the concept of resolution, smoothness, and all these other related concepts. So it really does make sense that some things are used more often than others. Other things, so if you look at the just how wavelets, how often they are used in peppers, and then I can use different sizes of wavelets, and then I can again plot how often is each wavelet used. So this is if I take 16 times 16 patches and it's 64 times 64 patches. This is not a log plot. This is now a log plot. And I've already also marked the line. How would the appearance probabilities be if it was equally distributed here? What you can see is really not behaving like that. Okay, they are not equally used. So we can use this model. It's easy, but it's not very realistic. And we also don't want it. We are happy that some things are more important, because if something is used with probability 1, I don't need to check, should I use this one? I just use it. So this is good, actually. But if we now want to sort of simulate our learning process and so on, it's maybe, you know, good to take this more realistic model into account. Good. So what we're going to do is we have a more flexible model. So what we can do is, if we didn't have to fix the support size, we could just make Bernoulli variables that we switch on and off. So with probability pk, they're on, and with 1 minus pk, they're off. And just to have on average S, we normalize them so that they sum up to S here. But then what we say is, okay, well, this is not always giving us something that has exactly size S, but we can just condition on the fact that we should only get supporters of size S. Basically, we flip all our switches. If we get exactly S on, we keep it. And if we don't get exactly S on, we trash it. So we just condition basically on the fact that S of these should be active. Good. And then what we also define is the inclusion or the appearance probability here. This is the probability that an atom is active. Okay. Now, this is more realistic. And the good thing is, well, this would be super nice. And this is basically the best we can get that is still realistic and close to super nice, because here everything is independent. But here we can basically pretend that we have the independent thing just by saying, if we have equality for Bernoulli, well, then we need an inequality for the Poisson sampling. And if we use pk's here, then we can use pi k's there. So this is basically what happens, and this is quite nice in handling after a lot of work. Good. So now that we have that in place, our model, we can have a little bit of intuition. Why do the algorithms work? So if you look at this here, we can say that, okay, y is actually phi x. So let's put that in. And then what we can see here, we have two types of matrices. We have the x hat that appears here twice. And then we have the hat matrix. So x is the true coefficients and x hat is the coefficients that I guess. Okay. So let's have a look what happens here. Well, here's again the matrices that I showed you. And then if you look at what this matrix A that I defined here, it's just I take all the x hat and then I sum a lot of them up. So probably this should go to the expectation here, right? And the same thing here. So let's have a look at what happens with this A matrix, okay? So we just have to remember how was the x hat actually built, okay? So we know how it is on the support that we choose. It is this thing. And then this thing basically says, blow it up with the zero so that it has the correct size. Okay, so we can put that in now, just in the definition. And what we get is this expression, which is just add that with this blow up thing, right? Good. Now here there's one thing that is complicated, and which is this expression. But if we assume that the sub-dictionary is really well conditioned and everything, then we can take the transpose of the pseudo-inverse. We can approximate this just with the matrix itself. Okay, so this should be okay. So what we get, that should be x transpose phi t ri, and here this is again the blowing up stuff. Okay, so this is perfect. And then there's another magic trick. So if I take phi I and I multiply it from the right with this blowing up matrix, what I just get is a diagonal matrix, which is 1 on this support I, and it's 0 everybody else, to get a really nice and easy expression here. So what we can have a look at now is what happens with this x transpose. Okay, so we just look at our model, what happened in there. And then if we just say, okay, let's take the expectation first over sigma. Well, here I have x of I times x of j, and we said that we have sign variables. So what's the expectation of this? Well, that's just 0. And then if I take the same thing for x of I squared, which is what happens on the diagonal, well, we said, well, that should be approximately 1, because here I don't have any sigmas anymore. Okay, so now we have to, this is just if I have the sigma. So what we still get, so we have to take into account, am I inside the active ones or outside? Okay, but if I just take the expectation over sigma and c, then we get that I get basically something again that is a diagonal on the active variables. Okay, so if I take the expectation now over everything, also over the support, basically what I end up with is this expression here that I just put in here. And now here you have to trust me that if I multiply from the left or the right with a diagonal matrix, I can also pointwise multiply with this matrix here. And on this matrix, on the diagonal, you have the probability that K is in the support on the diagonal. And off diagonal, you have the probability that two variables are in the support. Of course, that is much less likely than to have just one variable in the support. Okay, so basically this would be Pi times Pj, and this would be Pk. Then on the same time, you would think that if the dictionary is reasonably close, already the diagonal will have almost ones and the off diagonal will be small. So what you get is that this has diagonal dA, and here you have more or less something that is only on the diagonal, where it is all the pi's. So this should be really well approximated by just, multiplying the diagonals, because the off diagonal parts are in any case for both things small. Okay, so we get that here, and then you can do the whole thing again with the other one, and what you can say is I can also approximate this well, but here with the square. So let's plug that in here, and what you can get here is, so here we get phi, and then we get d alpha, d pi, and then we have to multiply with the inverse, so we get more or less d pi minus 1, d alpha minus 2. So these are all diagonal matrices, and the good thing is, if you have diagonal matrices, you can swap them. So what you basically get is you get phi times d alpha to the minus 1. So basically what we saw is, yeah, I'm going to get a real scaled version of my original dictionary. Excellent. And if you do the same thing here with the second one, you can also see that if I plug in the thing, so these are now both approximated by this. Now I have, so this thing cancels. And what I get here is now phi d alpha d pi. So again, a scaled version of what I actually want. So what you can see here is, yes, I mean, it makes sense. These things should work. Now, the hard part is making all the ideas why it should work into math, and that is very nasty and very long. But after that, you get with more or less this theorem. So assume that the signals follow the nice model from before, and we have all the things, and then we say, okay, we want now this diagonal matrix. So if our original dictionary is nice, so basically if I scale it correctly, then what I get is not too large. Okay, so this is, let's say, close to 1. Okay, and then the dictionary should not be coherent. So mu of something that is the max over I is not K, and here we take the inner product of phi I with psi j, and basically that measures for one dictionary how close two atoms are to each other. So how close is it to an orthonormal basis, even though it has more than d elements. So this should also be small, then things are fine. And now the second thing is constraints on the thing that we have, right? That should also just not be nasty, right? Again, here, should not be a horribly ill-conditioned matrix. Then it should not be coherent, because that is also bad. And then it should not be that even after resorting, that atom 2 is also close to atom 1. Okay, so if I compare these things, then they should be well behaved. So if that is done, then basically I will converge, and I will converge in a sort of combined norm. So both element-wise, I will go to 0. So each atom will approximate each atom, and also in the operator norm, or the scaled operator norm between the two dictionaries, I will get very close. Okay, so This is a bit hard to understand, but there's going to be some general idea. So this basically means I have a nice dictionary, okay? So this is the one, this is the psi I'm looking for. Let's go red here. And it is nice. It is also well conditioned. Now, what I need is that one of the ways to fulfill these things before is I'm already close. I'm close in this sort of combined norm. So the maximal distance in each direction here is not too far off. But then I also have to be sort of close in this other norm. Okay, so in this weird, let's say, this where things get meshed together thing. So in the end, what I get is if I start in here, no problem, I will converge. Nice. Wherever I start here, I mean, I can't exclude that I go like this, but I'm not going. I mean, experiments show you that you go actually like this, it will be fine. But what we also say is we can make this larger, okay? If we are in the far regime, we have the same constraints. So this will be okay, but I will get additional constraints, okay? So what I do not want is that it's coherent. So I have to take out certain things. Here, these are the coherent dictionaries. They are nasty. From there, I'm not going to get anywhere. And then I also have to ensure that they are sort of already close enough, let's say. So I have to take out these wedges as well. But in the end, what I see is if I start here, I'm going to go also to the thing that I want. Okay. Again, I cannot exclude that I'm going from here to here to here to here. Well, I get closer, so probably to here I cannot get, but still I will converge. Okay. I will tell you in practice from looking at things and not being able to prove them, but simulate them and then look at them, see this should be absolutely clear, but I can still not prove it 100%. You actually go the straight line. Okay. So can we have the same result for KSVD? I will not try. For me, it's good enough that the ODL was working. And the one that I showed you at the beginning, that is a bit easier to handle because it's a sort of, it's not quadratic, it's more L1. So that should be easier to prove more stuff for that. Then how likely are we to be in this convergent part? Not very. So with a random initialization, we're very unlikely to be there. But well, the random initialization is not totally off. So we have this sort of diagonal dominance, and we're not going to have it for the full dictionary, but if we accept a couple of atoms, both on the initialization side and on the original dictionary side, then this part will be diagonally dominant. So that's okay. So it will be partially diagonally dominant. And then this is quite far, but it means that the next goal is we can show that partially it will converge because the portion where we will be diagonally dominant is big enough and it's not going to disturb the rest too much. This is future work. And the good news is also it doesn't matter to do all these things to avoid these things because we have a quite good understanding of what happens actually in practice. And what happens is that, you know, two atoms look to the same original atom and then they both converge there. But what happens then is that this dictionary will be quite coherent. So, you know, oh, there's two things that are very, very close to each other. Let's just get rid of one of them. And then you can look in the residuals and find, okay, so what is missing? Okay. So it's actually nice because you get then this spurious local minimum where, you know, okay, one atom is double and then there's some other things happening. But now I can really jump to what I should be getting to. And we can do this for the very simple model where we have the uniform distribution, but we saw that is not good. So this thing that we have here is supposed to help us find out how to do this also in the more realistic distributions where we have a decay. So to jump from something that is redundant to something that's a bit better organized. Okay, so there's some reading material, so you don't have to travel home far. just for the lunch. So this is again the mod, online dictionary learning KSVD. Then this is a paper which gives you some early result for mod plus basis pursuit. They don't call the algorithm mod in there, but if you look at it, you see that is the mod, okay? It's a bit weaker and is for uniform distribution, more or less. And then this is the thing, if you want to have the results for the mod and ODL and see what is happening there. This is the paper that is available on arXiv. If you think, oh, there's some detail missing, I want it a bit more general, you can send me an email. I will give you a link to a master thesis where there is some further complications that you might be interested in. And now I've already gone over my time by 3 minutes. So thanks for coming and listening. And I'm happy to answer any questions that there still are.
Yes, thank you very much, Karin. Are there questions from the audience? So that maybe I can start with one. Can you tell us something more about the ITCAR-M algorithm, this other algorithm you mentioned?
Well, it's basically, so you just have to sum up things. So it's just, it's a very similar approach, but I don't have the thing on the top of my head at the moment, but well, how do we get, well, there's a piece of paper. Instead of, well, summing up, you can say, okay, I have always x hat, right? Transpose. And what you can do instead of doing that, you can say, I'll take phi, or this is sort of phi x hat. So we take y x hat actually. But these x hat, they are a bit wild. And they, you know, if you go wrong, they can go horribly wrong. But you can say, okay, let's instead take just the signs of x hat. And signs have the advantage that they're a bit more stable. I mean, they're sort of 0 or 1 or -1. And then you can replace this and this is behaving. So what you can see here, so this would be then the sign x hat, that this is, in the end, we have the x hat will be related sort of to x. So here we have something that is quadratic in, so we have some x transpose, which has a quadratic flavor, let's say, while here we have x sine x t, which has an absolute value behavior. So it's a bit more compact. It cannot go off that far. It's a little bit like the mean and the median, and the median is a bit stable. Also, let's say it's easier to calculate this in some ways. So it's very fast. And it's due to this having only the absolute value rather than the quadratic thing, bounding certain properties is easier. But I think this is the idea. And if you're interested, there's also convergence results for that. I can also give you more details. So if you look at the thesis of Simon, there is also the convergence of ITCAR-M, but you know, I've worked on this thing for quite a long time, so this is not as new and as exciting as finally having convergence result for mod and ODL.
Great. More questions?
Yeah, last question. So in when you do initialization, in principle, like you don't know which like permutation of the dictionary you're sort of, you might be close to. So in principle, you need to think of like actually when you look at all these pictures where you have these convergence regions, you also want to think about like all possible permutations. So actually a union of all these regions.
Yeah,
here.
but this is, I mean, I can always assume that I have the renumbered thing, right? I just need to mentally renumber, and then that's fine. So I don't actually assume that phi psi is diagonally dominant, but after some permutation of some reordering in phi.
Right.
But
So
for analysis, that doesn't change it. It's just still that you have some sort of locality issue. And you've always have to think of this last slide as, sorry, oh, well, wrong direction, sorry. You can think of this as tiled. So there's the same picture here for some permutated phi. And then with your psi, you're going to be in one of the slots, let's say. And that will have the same image here, and it doesn't matter where you are. You will converge to something that is equivalent.
Yeah.
So it's really just reduced to the essential picture.
Okay.
So I didn't mention that, but I assume we've done the reordering mentally in the back, and we prove convergence to some sort of resorted phi. But well, let's for simplicity assume that was the original one. Okay.
So there does not seem to be more questions from the audience. Then I would like to thank the speaker again. And to everyone listening, we will be back in 3 weeks with another Eurasian 1W-minds seminar.